in a 100 million parameter model, how many of those weights might be relevant for the image skateboard?
Yeah, and that's one of the open questions is what is the minimum amount of number of weights you needed to solve this problem, right? And so there's this idea of a model being over parameterized, meaning it's bigger than it needs to be. But because we don't have ways to interpret the model, people just keep making it bigger, hoping that, well, if we have bigger models, then we increase our chances of finding the optimal weights that will solve this problem. But so what if 80% are garbage? As long as we have the 20% that do the job, that could still work. And in many cases it does, but it's just wasteful.
Welcome to Practical AI, everybody. My name's Jeff. I'm here with Peter Lin. Practical AI is brought to you by Pocket AI. Pocket AI is a tool you can use to prune your models without loss in accuracy. Visualizing your models and your model weights is akin to a brain surgeon being able to find individual neurons and removing them without harm to the brain. Similarly, Pocket AI allows you to analyze and prune the weights in your model to select the right backbone model, get that model to actually work, make your model more stable, increase your model's accuracy, decrease the size of your model by up to 60%, and put that smaller model into production for half the cost. You no longer need to continue with endless brute force training and new model trials. Pocket AI allows you to perform brain surgery on your existing models, making them smaller and better. Peter, we want to kind of tackle a difficult topic today, at least difficult for the people who are not deep in this field, and that is gradient descent. It's something that even the novice person hears from time to time, but it doesn't really mean anything to us. So tell us a little bit about gradient descent, why that word is used, and what role it plays in machine learning.
Yeah, so the concept comes from math, right? And as far as like computer science goes, it's used to basically optimize a model. So basic idea is the model starts with random weights, and then you want to get all those weights towards the optimal value. And so what you do is when you run it through, you do a prediction. It says, okay, it's A, B, C, or D, and when it's wrong, you can use one of the many loss functions to figure out like, okay, well, it was wrong. How much do we adjust every single weight going back to the front so that it gets better? And so like in the case of CFAR, where there's 10 classes, you put things through, it gets the wrong prediction and it goes, okay, it got it wrong on like 3 different things and it didn't get the actual correct one. So it goes, okay, I'm going to adjust all these weights. And so this is the idea that with gradient descent, you're trying to get all the values, all the weights, all the parameters to the optimal value. But what happens is as you're making changes, you can overshoot the value that you want. And sometimes it can get trapped in another valley. And so there's an old video by 3 Blue 1 Brown where they explain how machine models learn. And so they have this kind of graph with a couple of dips, a couple of valleys, right? And so classically, when people think gradient descent, they think just of a simple value like a half pipe. But in reality, it's not that. It's much more messy than that. Because as these 10 classes are coming through, what happens is it makes these adjustments and it ends up not being in the ideal valley. It might be in some other valley that's not the one it needs to be. And then it gets trapped in there. And then in that case, it becomes like a roadblock.
Okay, so we're going to pull up that visual because it is very helpful. So let me just kind of repeat back what I think I heard, and you can edit it. So ultimately, like in the case of CFAR, that's a data set of 10 different classes of animals or images. And as that data set gets, as the model trains through that data set, it's going to make predictions as to whether or not this is a cat, this is an airplane, this is a dog,
Right.
whatever. And then it gets yes or no, or how far off, or whatever. So
Yep.
ultimately, there's a prediction, it got it wrong or right. And so that means that if we boil it down, just not from the model level, but all the way down to each individual neuron or weight or parameter, that parameter got it right or wrong. And The gradient descent calculation or formula is basically saying it's wrong, and it's either wrong by this much or whatever, but we're going to guess that if we adjust, we're going to get
Yep.
closer.
Yep.
And it doesn't know what the value is supposed to be, but
No.
it knows that it's wrong. And so it's going to try to do some math and figure out if it can get it more right. And the
Yeah.
idea is over time, all these training runs, that it gets closer and closer and closer to that ideal value, whatever it is,
Yeah.
so that that particular neuron fires and gives the right value. Is that essentially what we're talking?
Yeah, I think if we use a game like 20 questions, right? So basically, graded descent, depending on the loss function you choose, is trying to answer, is trying to figure out a game like 20 questions. Someone says, I'm thinking of something, and then you ask it, is it, you know, is it an animal? Is it metal? Right? And so you keep asking questions and you try to figure out like, what is this thing that this person is thinking of that you don't know? And so graded descent basically tries to figure out like, well, okay, of these possible things, where should it be?
Okay, so we'll use 3 images from this YouTube video that that we'll include in the discussion box. But here's an example where there are 3 valleys in this. This is actually a function, a curve, right? But just imagine 3 valleys here. And if we say that the valley on the far left is actual, the bottom of that valley is actually the ideal value, you can see here that this this value that it's kind of locked in on here, that yellow part, is not only in the wrong valley, but it's not at the bottom of the valley,
Yeah.
right? And if the bottom of the valley is the ideal spot on the curve, if this value for the parameter, the weight, was given, it would be wrong, but then the gradient descent process would say, you should get closer to the bottom, and here's a adjustment you can make to get
Right.
closer.
Yeah. And so in this case, right, like chances are it's going to try to get to the bottom of that middle valley instead of the correct one.
Correct. And this is where it's kind of good, but not awesome. It's
Well, but that's the tricky part is like, we don't know if it's good, bad, or awesome. And so, and that's part of the difficulty of how do you understand weights on a model is, well, it could be in one of these 3 or 4 different places, but how do we know?
yeah. So here's the example where here's the 3 bottoms essentially,
Yep.
and if we locked in on that middle one, it might be the wrong value.
Yep.
And this is not just 2-dimensional, this is 3-dimensional, and this is where it gets complicated. Whoops. We'll get through the commercial, but essentially this becomes like a 3-dimensional skate park at some point.
Yeah, it does.
And we're trying to find the bottom in multiple different zones.
Right. Because every single weight has potentially one optimal value. Right. And so obviously this is why kind of when you train a model, it takes billions and billions of calculations and weeks and months to train these models because it's blindly trying to find the optimal value for every single weight. But the difficult part is it's not that it's just one weight, it's that all the weights are related from layer to layer. And groups of weights within a layer also are related to a group of weights in another layer. And so this is complex interaction of weights across layers that are working together. And if let's say layer 2 has a roadblock somewhere, well, things aren't going to flow, right? It's like a traffic jam.
Well, and I think you and I were talking earlier about this too, in a 100 million parameter model, how many of those weights might be relevant for the image skateboard?
Yeah, and that's one of the so open questions is what is the minimum amount of number of weights you needed to solve this problem, right? And so there's this idea of a model being over parameterized, meaning it's bigger than it needs to be. But because we don't have ways to interpret the model, people just keep making it bigger, hoping that, well, if we have bigger models, then we increase our chances of finding the optimal weights that will solve this problem. But so what if 80% are garbage? as long as we have the 20% that do the job, that could still work. And for many cases it does, but it's just wasteful.
And then not only is there a minimum number of parameters, weights that are necessary for the skateboard image or whatever. Also, you're saying that sometimes the values of other weights, parameters that are not related to skateboard, they can interfere
Oh, they do.
with.
Yeah, well, because when the last function calculates, okay, so answer is supposed to be B, and it got non-zero values. So let's say E, F, G, and H had values that were 0.5, 0.9, 0.8, 0.7. So it goes, okay, well, all of those are wrong. It was supposed to be A. And so now we're going to like adjust all the weights going back to the front. And it's probably going to overcorrect because there's 4 different values that I thought it was. None of them were correct. And so it got 4 things wrong. And so now it's trying to correct for 4 different things. So like, how do you adjust for those 4 different things that were wrong? So there's conflicting interests. And as you back propagate all these little adjustments, chances are it's going to get it wrong. But the hope is that if you do a billion times or a trillion times, it'll eventually figure out the right one. But it doesn't.
Then don't some models catastrophically collapse and overfit and all the things
so
that
people just
happen?
do multiple runs.
Yeah.
So you do one run and it pukes out. You go, well, okay, I'm going to try a different random seed. I'm going to run it again. And then you just run it until you get a good one.
And then you stop once it goes from good to catastrophically failing.
Right. So this is concept of so in training models, you can have it fail or basically stop the training process. Let's say I set it to train for 200 epochs. It's easy to detect if it's failing catastrophically. You can stop it so you don't burn your wallet because like if it got to best state by epoch 20, you don't want to run the other 180 because you're paying for it.
Yeah, that's a good point. So right now, the method, there's gradient descent calculations and methods that are applied.
Yeah.
But then the way people are really just getting there is more training, more data, bigger models at this point.
Yeah, if everyone picks like the top 5, top 10, or top 20, and they do a bake-off, right? They go, okay, same data set, 20 models, train them all, see which ones score the best, pick the top 5, try to improve those 5, keep repeating it until you get to the point where it's good, and then you hope that the next time you need to improve the model again, that one still works. But if it doesn't, you go back to the other 5 or the other 4 or the 3 that were pretty good, and you try again with those.
Okay. Well, you've got some clever tricks on how to improve the process, and we'll get into that at another episode. But this is great. It's great to learn about one of these concepts that we hear so much about, but isn't easily understood by people who aren't in the industry. So, Peter, thank you. Good lesson today, gradient descent. We'll come back next time with another topic. And in the meantime, you can follow us on Spotify. We're there. And always ask us questions, and we'd be happy to answer them. Thanks, everybody.